section 4.2. In this section, we deal with so-called autonomous systems of differential equations. Autonomous means on the right-hand side, there is no t. You can see it here. No t here, and so no t here. For example, going back to section 3.1 over here. So this is not an autonomous system. We have t. However, over here, this is an autonomous system. There is no t. This is an autonomous system. There is no t. Basically, most systems that we discuss in this course are autonomous systems. Any system that can be written as x dot is equal to ax is an autonomous system, because on the right there is no t. Now, definition. The solution phi of t of our autonomous system is stable if every solution psi of t, which starts sufficiently close to phi at t is equal to 0, must remain close to phi for all future time. In simple words, a solution is stable if it does not drift too far from any other solution of this system. Let me give you an example. Please take a look at, for example, this system. The general solution of this system is this. Since the components of these matrices are sines and cosines that are bounded functions, all solutions are stable. Indeed, if you plug in some values for C1 and C2 to come up with a particular solution number 1, and then some other values for C1 and C2 to come up with a particular solution number 2, these solutions will never drift too far from each other because these functions are bounded. To the contrast, please take a look at this system. The general solution of this system is over here. And now, if you plug in some values for C1 and C2 to find particular solution number 1, and then some other values for C1 and C2 to come up with a particular solution number 2, these two particular solutions will go farther and farther and farther from each other because e to t's power is growing without bounds. So all solutions of this system are not stable. The next theorem shows us how to determine whether or not solutions are stable or unstable without solving our systems. So theorem 1. In theorem 1, we are talking about these systems only. We are talking about systems that can be written as x dot is equal to ax. Every solution of this system is stable if all the eigenvalues of A have negative real part. Well, here's an example. Please take a look at this. We have the following system of equations. By the way, we will not discuss in this course asymptotic stability. We will discuss only stable or unstable. So Here's a system of equations. We find all eigenvalues. It turns out that eigenvalues are -1 and -1 plus minus 2i. Note that in all three cases, the real part is negative. Therefore, all solutions are stable. You may ask me a question, why is that? If you write down the general solution of this system, you will see that for each particular solution, we have e to negative power because a real part is negative. This guarantees that all solutions converge to each other because e to negative power converges to 0. So all solutions are stable. Case B. If there is at least one eigenvalue that has positive real part, all solutions are not stable. Please take a look at this example. In section 3.8, we found the general solution of this system. Here is the general solution. Over here. Obviously, the solution is not stable because we have e's to positive powers. But once again, Theorem 1 allows us to conclude that all solutions are not stable without solving the system. We just look at eigenvalues. Both eigenvalues are positive, therefore all solutions are unstable. Before we jump into C, do you have questions about A and B?
When we say stable, we mean a negative coefficient in the particular solution. However, if we have unstable, it means positive to the coefficient in the particular solution.
So we are not talking about negative or positive real part of a solution. We are looking at positive or negative or real parts of eigenvalues. In other words, step 1, find all eigenvalues. Step 2, look at their real parts. If all real parts are negative, all solutions are stable, which means they do not drift far from each other. It's exactly what we do in this example. Step 1, find characteristic polynomial. Step 2, find all eigenvalues and look at their real parts. In all three cases, for lambda 1 and lambda 2 and 3, all real parts are equal to -1. Therefore, all solutions are stable. However, in this example, we find characteristic polynomial. Eigenvalues are 6 and -4. One of these eigenvalues has positive real part. Therefore, all solutions are unstable. Was that your question?
Yes. Could I ask a second question? So let's go to one of the particular solutions for the eigenvalues.
You want to look at a particular solution of a system, correct?
Yes.
Yes. So let us take a look. Let us go back to this system. Here is a system. Here is the general solution of this system. Note that looking at this formula, we see that all solutions are unstable because they drift far from each other, because e to positive power goes to infinity. Means if you consider one particular solution, plugging in some values for C1 and C2, and then consider another particular solution, plugging in other values for C1 and C2, these two particular solutions will go farther and farther from each other.
When we have a positive coefficient for E right here.
You're talking about 1 and 5.
Yes, so for the positive eigenvalues, are we assuming that T cannot be negative here?
No, we assume that t is positive. So this is important. It's written for all future time. T goes to positive infinity.
And so when the eigenvalue is negative, it's going to negative infinity.
No, it goes to 0.
Ah, I see.
If, for example, instead of 1 and 5, we have -1 and -5, all solutions are stable, because if t goes to infinity, e to negative t goes to 0, and e to -5t goes to 0.
Yeah.
You see it now?
Yeah, I see it now.
So therefore, looking at this example, if both eigenvalues are positive, all solutions are unstable. Moreover, if one eigenvalue is negative, but the other eigenvalue is positive, again, all solutions are unstable because this term goes to infinity. Only when all real parts of eigenvalues are negative, only in this case, all solutions are stable. Does this answer your question?
Yeah.
Other questions?
For something being stable, could you think of it as like, as t goes to infinity, you can bound the solution like with an upper bound and a lower bound?
Well, it's exactly what I was talking about here. So please take a look. Let us go back to section 3.1. Please take a look at this example. Over here, we have this system of equations, and here is the general solution. All components are bounded functions. All solutions are stable. They cannot drift far from each other because sine and cosine are between -1 and 1. Does this make sense?
Yes, thank you.
But now, guys, please take a look at C. In A and B, we are talking about positive or negative real parts. Question: what if there are eigenvalues where a real part is equal to 0? Here's what we do here. If there is an eigenvalue where a real part is positive, all solutions are unstable. Therefore, let us assume that there are no eigenvalues where real part is positive. This means that all eigenvalues have either negative real part or 0. Here's an example. Please take a look at this. Here's our system. Characteristic polynomial is lambda squared plus 6. Eigenvalues are 0 plus minus square root of 6i. So all eigenvalues have 0 or real part. What do we do in this case? In this case, we find multiplicities of all eigenvalues with 0 or real parts. And then we look at the dimensions of the corresponding eigenspaces. If the dimension of the corresponding eigenspace is equal to multiplicity, all solutions are stable. If there is an eigenvalue, multiplicity of which is bigger than the dimension of the corresponding eigenspace, all solutions are not stable. It's exactly what we have in this example. Observe that we have two distinct eigenvalues. Since these are distinct eigenvalues, multiplicity of each eigenvalue is 1, because a lambda square plus 6 can be rewritten as a lambda minus square root of 6i times a lambda plus square root of 6i. So in both cases, multiplicities are equal to 1. And observe, the dimension of each eigenspace cannot be lesser than 1. So multiplicity is equal to dimension, therefore all solutions are stable. And the explicit formula confirms our conclusion. Since all components are bounded functions, all solutions are stable. Any questions?
Do you mind going over part C of Theorem 1 one more time?
Yes, absolutely. So part C is very confusing. Step 1, find all eigenvalues. Step 2, look at their real parts. If there is a real part which is positive, by B, we immediately conclude that all solutions are unstable. Case 2, suppose there are no real parts that are positive. In this case, there are two subcases. All real parts are either negative or 0. If all real parts are negative, all solutions are stable. But now imagine that some real parts are 0. What do we do in this case? In other words, suppose that there are no positive real parts, and suppose that not all real parts are negative. What do we do in this case? In this case, step 1, find multiplicity of each eigenvalue with 0 real part. Indeed, since here we have just I times sigma 1, our real part is equal to 0, because a complex number can be written as alpha plus beta I. Here we have only beta I, there is no alpha. A real part is equal to 0. Find multiplicities of all such numbers. Then find dimensions of the corresponding eigenspaces. If each multiplicity is equal to the dimension of the corresponding eigenspace, all solutions are stable. If there is an eigenspace, dimension of which is lesser than the corresponding multiplicity, all solutions are unstable. How is that?
How do you find the dimensions? Could you give me like an example?
Well, we just go back to previous examples. So let me start with section 3.8. Let us consider this problem. How do we find dimension of each eigenspace? So we find all eigenvectors corresponding to lambda is equal to 2. We split this matrix column into the sum of two pieces, and now we see that each of these eigenvectors can be written as a linear combination of two linearly independent matrix columns. Therefore, the dimension of this vector space is 2. For lambda is equal to 9, the dimension of the corresponding eigenspace is 1, because each matrix column is a multiple of this matrix column. Does this answer the question?
Yeah, and when we're applying Theorem 1, do we find the dimension of the matrix that we find the eigenvalues of?
We find the dimension of the corresponding eigenspace. Here's matrix A. We find all eigenvalues. Then for each eigenvalue, where a real part is 0, we find the corresponding eigenspace. And then we find the dimension of this eigenspace. In the same fashion as we did over here, there are 2 eigenvalues, 2 and 9. For each eigenvalue, we find the corresponding eigenspace, and then we find its dimension. Here dimension is 2, here dimension is 1. So in C, step 1, we find all eigenvalues where a real part is 0. It's over here. Then we find the corresponding eigenspace for each of these eigenvalues. And then we find its dimension. Lastly, we compare dimension with multiplicity. If dimension is same as multiplicity, all solutions are stable. If there is an eigenspace, dimension of which is lesser than multiplicity, all solutions are not stable. Did I answer the question?
Yes, for the most part. And how do you find the multiplicity?
Very good question. So please take a look at this example. Over here, we have parentheses without any power. Means power 1. Means multiplicity of -1 is 1. Similarly, this polynomial can be rewritten as lambda minus lambda 2 times lambda minus lambda 3, where lambda 2 is -1 plus 2i and lambda 3 is -1 minus 2i. And each time we have first power again. To the contrast, please take a look at this characteristic polynomial for this matrix. It's negative lambda squared times 7 plus lambda. Multiplicity of 0 is 2. Multiplicity of -7 is 1. Does this answer your question?
Yes, thank you.
Other questions?
Professor, what if the dimension is greater than the multiplicity?
Another excellent question. One can show that the dimension of the eigenspace cannot exceed the multiplicity.
Okay, that does make sense.
Other questions?
I wanted to talk about a two-dimensional eigenspace.
Yes, suppose we have an eigenvalue such that the corresponding eigenspace is two-dimensional.
Yeah, I wanted to particularly talk about two-dimensional eigenspace for a particular solution where lambda is equal to some form of alpha plus or minus beta I.
Yes, okay. So suppose a lambda is complex.
Yeah.
So here's the thing, let me give you a quick answer. We will not discuss these questions here because if an eigenvalue is complex, the characteristic polynomial will have as a root its conjugate necessarily, which means if alpha plus beta I is an eigenvalue, the characteristic polynomial has another root, alpha minus beta I. Note that these are different roots since beta is not equal to 0. Correct?
Yeah.
Now, suppose root number 1 has multiplicity 2. The second conjugate will necessarily have multiplicity 2.
Yep.
So we have two terms of the form lambda minus lambda 1 square, lambda minus lambda 2 square. Therefore, the degree of our characteristic polynomial will be either 4 or bigger, which means the corresponding system will be 4 by 4, or bigger, we will not discuss this case in this course.
Yeah, makes sense. Could I ask a second question relating to
Okay.
this?
Sure.
Let's say that alpha is greater than 0, so it's positive.
Suppose, give me a second.
Sure.
Note that in this theorem, we are talking about real parts only. So by alpha, you mean a real part, correct?
Yes.
So suppose we have an eigenvalue which a real part is greater than 0. Okay.
So in this case, it would be unstable, right?
Yes, all solutions will be unstable.
Okay. Yeah. I was just wondering that. Thank
Yeah.
you.
Absolutely.